Okay, so our first end of chapter practice problem is a synthesis. In a second, I want you to pause the video and try to work through it on your own, or pause the slideshow. If you don't have an idea, you can unpause it and I'll give you a hint, and then you can pause it again and keep working forward. So go ahead and push pause. Okay, if you're back for a hint, maybe you notice that the starting material is acetoacetic ester, and acetoacetic ester is used to make a methyl ketone. So here's a methyl ketone. Here's our alpha carbon from acetoacetic ester. This must be what we added on to it. So go ahead and push pause and see if you can work through it now. Okay, so hopefully you managed to get through this one. It shouldn't be too bad. So this is an acetoacetic ester synthesis. We're trying to make a methyl ketone. So we're going to start off by deprotonating. So a reaction with ethoxide would give us an enolate. And now all we have to do is figure out what we are going to add on. And that's going to be this portion. So we need that. And a leaving group. So I'm going to pick an acyl bromide. It could be an acid chloride. It could be whatever, as long as you have the halogen directly attached to the carbonyl carbon. So this one's actually going to work through, a tetrahedral intermediate. And then we would kick out the bromine. And then you would hydrolyze it and get to your product. Oh, I started writing diethylmelanate. Dang it. Okay, so then you would hydrolyze it and you would get to your product after you decarboxylate it. But remember that this is a synthesis, so you don't typically draw out the mechanism. I chose to draw this one out because we hadn't done a reaction with an acyl halide in a while. So let's go ahead and erase. And let's actually write this out like you would write a synthesis solution. Okay, so in a synthesis, remember you give the reagents and the intermediates. But you do not need to draw out a mechanism. And then from here, H3O plus and heat would hydrolyze our ester and then decarboxylate the carboxylic acid. So that would be our synthesis. You'd also be welcome to combine these two on one arrow if you wanted by doing first step base, second step the electrophile in your substitution. So you could have done this in just 2 steps if you really wanted to. Okay, this one is not a synthesis, this one's a problem. So again, I'm going to give you a second to pause and then try the problem on your own. And then if you need a hint, you can unpause and get the hint from me. Okay, so if you're back for a hint, my hint is that in step 1 you have methoxide and you have a methoxy ester. So that must mean that you're doing a deprotonation to form an enolate. And now you just have to find where is your most acidic alpha hydrogen, because there are multiple alpha hydrogens here. Okay, so let's talk solution. If you're not done, push pause. So we have 2 alpha hydrogens present, right? We have the one that's to the left of the ketone, and then we have the one that's in between the ketone and the ester. I was going to ask which one to use, but this is a video, you can't answer me. So the one that you should use is the one that's between the 2 carbonyls. It's significantly more acidic. So when you react with the sodium methoxide, remember we're not worried about the sodium, it's the methoxide that we want. After step 1, you're going to have an enolate. And then in step 2, you're adding in an alkyl halide, or an alkenyl halide actually. So this is going to be a substitution reaction. Your enolate is going to attack, you're going to kick out your bromine. So after step 2, you have the same giant compound and you're adding on 1, 2, 3 carbons, and don't forget your double bond. I'm going to clean that up in a second. So this is a really good time to do some carbon counting if you're not typically good at carbons, or counting them, I guess. So we drew the original compound back out, and this has 1, 2, 3 carbons. So 1, 2, 3. Make sure that you're connecting in the right spot. A common thing that I see in problems like this is people just putting the alkene in the wrong spot because they just weren't counting and thinking about which carbon was actually being attacked by the nucleophile. So then step 3 says hydrochloric acid, water, and heat. So when you see that, you might think, oh, I've seen, hydrochloric acid and water react with an alkene before, but this is hydrochloric acid, water, and heat. This is aqueous acid and heat. We are trying to hydrolyze the ester, and then it's going to decarboxylate because of the heat. So what we're going to end up with is our ketone with our alkene added and carbon dioxide, which I know we haven't really been drawing in, but that is going to be one of the side products. So this was very similar to like a malonic ester synthesis. It's just using a ketone and an ester instead. Okay, go ahead and pause. Okay, if you're back for a hint, what is the name of this? This is sodium plus and H minus. What is this guy and what is it used for? So our reagent here is sodium hydride. Now we've mostly seen hydride for use in reductions with carbonyls, but towards the beginning we also saw it being used as a base, and mostly we saw it being used in deprotonating like a terminal alkyne or something. So it's a strong base. It could also function as a nucleophile if you wanted it to. But you have to ask yourself, what reaction is faster, deprotonation or nucleophilic substitution? And the answer is deprotonation. Deprotonation is so much faster. Nitriles were on that list of things that count as activated hydrogen compounds. So this hydrogen is quite a bit more acidic than any other hydrogen on this molecule. So if I pull off this hydrogen, I can put those electrons back onto that carbon. I'll have my chlorine. And a carbanion and a nitrile. So then I have this carbanion. That's definitely a good nucleophile. There's no other reagents provided to us. So the only thing it can do is attack itself, right? It's going to kick out the chlorine, and we're going to end up creating a cyclic structure. Now remember, if you're not super great at counting, make sure that you number your carbons. So 1, 2, 3, 4, 5. We're going to have a 5-membered ring. And you could go back and number those if that helps you. Doesn't really matter where you start your numbering because it's a ring. And then off of carbon number 1, I'm going to have my nitrile carbon, my triple bond, and my nitrogen. So a pretty cool way to make a cycloalkane that has a nitrile coming off of it. Okay, go ahead and pause. Okay, if you need a hint, look up LDA, on Google or in the index of your textbook. What do we use it for? What is LDA? Okay, so LDA is lithium diisopropyl amide. It's a very strong and bulky base. So it's not going to be able to act as a nucleophile. It is only going to act as a base. And it's going to be interested in that alpha hydrogen. So LDA in case you don't remember the structure, I'm going to make an enolate. So now I have an enolate, which is a good nucleophile, and then I have an acyl compound that doesn't really look like something that we've used before, but you do know what to do with an enolate and a carbonyl compound. You've seen that already in this chapter. So I'm going to attack that. And here's my carbonyl carbon. Here's my oxygen, chlorine, and I have ethoxide. You've seen this type of tetrahedral intermediate before. Both chloride and ethoxide would be pretty decent leaving groups, but if you recall which carboxylic acid derivative is the most reactive, it was the acyl chlorides. They were significantly more reactive than esters. So the chloride is going to be the better leaving group. So I'm going to kick that out. And then that means that after step 2, I have an ester. And then step 3 is just a typical workup step. Water is not going to do anything to an ester or to an aldehyde. So final product. Okay, go ahead and pause. Okay, if you need a hint, my hint for any problem that you get stuck on is to not really think about the product, especially if you're looking at a mechanism. You know, look at your starting material and look at your reagents and what can you do with those. Usually those options are pretty slim. If you need a second hint, you may be debating whether or not to do some sort of chemistry with the alkene. You know, take a look at the product. There's no oxygen present on those carbons in the product, so nothing from the alkene is, you know, adding anything other than a hydrogen, really. And also notice that the hydrogen count in the starting material and the product is the same, so there's no overall net gain of anything. Okay, so that last hint was actually really the big one. There's no net gain. So this tells you that this is a protonation, deprotonation type situation, or maybe a deprotonation, protonation. This is actually done through tautomerization, essentially. So we have hydroxide and we have an alpha hydrogen. Our first step is just pulling off the alpha hydrogen. To create an enolate. And I went ahead and put the electron density on the oxygen. I was kind of on autopilot. That's something that I usually did in undergrad. It doesn't matter. We were going to draw the resonance form anyway. If you're wondering why we didn't take the alpha hydrogen from the other side, it's just because both of these hydrogens are probably getting pulled off in equilibrium, but it's the blue one, the one on the right-hand side, that is actually going to move you towards your product. So what you may notice is that in this structure now, we have a conjugated system. So what that means is if we were to swing these electrons down, push those down, we could then push these pi electrons onto that carbon. This would be a resonance form. Where we now have a negative charge on that methyl group. Now, hopefully, looking at this, you're like, oh dang, that looks a lot like the product, right? So all we have to do is protonate. So this is essentially a tautomerization between there's several different keto-enol forms. Yeah, and then with this one, you could also, there might have been a lot of trial and error. Maybe you didn't immediately put the electron density onto the oxygen. maybe you started there, you could have still pushed those electrons onto that methyl group. You still would have gotten to the same place. So. Okay, go ahead and push pause. Okay, if you need a hint, the first part of this synthesis has nothing to do with this chapter. It's actually that you have to turn this into something that you did use in this chapter. So you have to go back several chapters in OChem 2. It's one of the first things that we did. We looked at alcohols and we turned them into something else. Another hint would be that ultimately this is a methyl ketone. Where have we seen methyl ketones today? By today, I mean this chapter. This is all today for me. So, if I'm doing a synthesis problem, I kind of look at starting material and I look at the products and ask myself, what can I do with these things? So looking at your starting material, a diol, the options of what you could do with that are just completely endless, right? But in order to create some sort of substitution on an alpha carbon, those options are pretty limited. And since this is a methyl ketone, I would say that this is probably using the acetoacetic ester synthesis. So before this step, I would assume that I had an ester. And I hydrolyzed and decarboxylated. Oops, that said neat, not heat, although this is pretty neat, to get to the ketone. So, whoa. Sorry, as I said, this is all today for me. I should probably push stop and start over on this slide, but you know what? We're just going to roll with it. So, I have my ester. I'm going to hydrolyze and decarboxylate. Now, this looks a lot like a problem that we did in this chapter, right? So before this, I somehow have to add on a ring. I have to add on these 3 carbons, but the alpha carbon is going to end up part of the ring. So this might look really familiar. If I want to make a connection, let's say we're making this bond here. Those 3 carbons would have to be on there already, 1, 2, 3, and some sort of leaving group. And if I added in ethoxide, I could get an enolate formed on the alpha carbon and it would kick out the bromine and close up my ring. Remember, this is a synthesis, so I'm not drawing in a mechanism or anything. I'm expecting you to be able to kind of plug and chug that into your head. So at this point, you could keep working backwards or you could start working forwards. Hopefully by now what you've realized is that you have to take this compound and somehow turn it into acetoacetic ester. So the first step in that would be an oxidation, right? We need a ketone and we need to eventually get to an ester, but we can't just go straight to an ester, but we can make a carboxylic acid and turn it into an ester. This is from maybe 2 chapters ago. So we're going to need ethanol in excess and acid. And now I have acetoacetic ester. Now if I add in ethoxide and follow it up with 1,3-dibromopropane, I'll have everything I need. Pretty fun, right? Now you guys are getting towards the end of OChem. Hopefully this is just turning into like one giant puzzle for you, and maybe it's becoming fun, I hope. Okay, this one's pretty cool. There's actually a whole bunch of different ways that you could do this. So go ahead and push pause. Okay, if you need a hint, obviously there's some aromatic chemistry going on here, right? Look at the substitution. Is this ortho, meta, para? And what does that degree of substitution mean for the order in which you have to add on your bromine? So, currently, if you take a look at this problem, currently we have kind of a confusing substitution here. This doesn't really look like any of your traditional ortho-para directors or your meta director. If you want to be just 100% sure that that is going to be a meta director, you could go ahead and oxidize it. You could keep it gentle and turn it into a ketone. And then add in bromine, and iron tribromide. Put your bromine on in the meta position because we know for sure that ketone is a meta director. So from here, I mean, you could either use chemistry from chapter 18, or you could just blow past chemistry from chapter 18 and go crazy. So now that we're at this point with the ketone, you kind of have to proceed with chapter 18 chemistry. So what you could do from here would be to add in a huge excess of bromine and an excess of hydroxide. That would be the haloform reaction. So that we end up with a carboxylate, because an amide is ultimately a carboxylic acid derivative, so we kind of have to go through a carboxylic acid derivative to get there. And then you could protonate it to get it to the carboxylic acid and add in thionyl chloride. And then if you added in an excess of diethylamine, you could get to the product because it would substitute on the acyl chloride, and the excess would just be to deprotonate your intermediate there. There are several different ways that you could do this, so we could backtrack. That's one option. Okay, erasing takes forever when you've drawn a ton of tiny lines here. Okay, so something you could do. You could jump ahead big time if you wanted. Use Jones, get straight to your carboxylic acid. Go to your acyl chloride. Make your amide. Which is also a meta director. although quite a bit more deactivating than your ketone would have been. But that would get you to your product. Another one, let's see. I thought I had another one. I guess you could change the order in which you add on the bromine, but ultimately those are kind of your options here. So anyway, that is the end of the chapter 18 practice problems on this video at least. So I hope you found this helpful.